Yeah, you can start recording right now.
Okay.
We are going to record the whole workshop. We'll be taking some pictures. If anybody has any kind of objection, now is a good time to tell us. If you, I don't know, don't want to be in the pictures or anything like that. Any objections?
Are you going to do Photoshop afterwards?
If you want, yes.
Okay, so with that out of the way, I think we are ready to begin in about 1 minute. And before we do, I just want to say thank you all for coming and for submitting your work to our workshop. And I'm looking forward to hearing about your work in just a few minutes. One, two, three. Can you hear me? Is that better?
Yeah.
We have the thing there. Maybe we can make it louder. Is this good enough?
Yeah.
Okay. Okay. Shall we start?
Yes.
Okay. So welcome to the Embedded Vision Workshop at CVPR 2024 in Seattle and online all around the world. My name is Branislav Kisachanin. I'm one of the organizers. Let's see if I can flip my slides. Can I? Okay, here. So we have Nabil right there, Seway, myself. Marius is not here with us today. And if you need to see the program, the times and all that, you can QR code this thing. It will take you to our website, and the latest program is right there. And you will see that QR code throughout these slides. So don't have to do it right now, but now is a good time as any. Okay, flip the slide. Okay, we have 5 invited speakers. It's going to be really great to hear about their work. We have Yusuke Sakemi from Japan, Zoran Kostic from Columbia University in the US. We have Mario Munich from Embodied in US. We have Marilyn Wolf from University of Nebraska, Lincoln, also US. And Jan Ernst from Latent AI, also US. I'm looking forward to their presentations, and you'll see it's all really good stuff. I don't expect you to read this program, but I want to point out the challenge we have with posters. Posters are on the 4th floor in that huge room 4E. I'm sure most of you already went there to see it. There's going to be a 5-minute walk there, 5-minute walk back. And I apologize for that. That's just the cards we were dealt with. And we'll make sure we follow the times. Okay. So we'll have presentations here. We'll walk to the poster room, more presentations, another poster session for the papers that were introduced in that second part, and then again come back here. So a little bit of exercise, okay? All right, about the presentations, we will record everything. Nobody had any objections about that. The workshop videos will be available at CVPR at some point, their virtual platform. Invited talks will be 20 minutes for the talk, and I'll gently remind our speakers at 20-minute mark to wrap up if they didn't already, and then 5 minutes for questions. The papers will have 3 minutes to do their spotlight presentations, and your slides will be timed. You don't flip them, they flip themselves, if I did everything right in PowerPoint. And later you'll have your poster sessions. We will announce at the very end the best paper award based on the reviews at the time, when we had the reviews online. Online participants, please send your questions through the Zoom chat box. Please provide your email. If we don't get a chance to respond to your question, we will see your email and we'll make sure the speakers reply offline. And that's that's basically it. I don't think I missed anything important here. And we are ready for our invited speaker. Please join us here. And let's see if I can put this up here so you can flip the slides yourself. Okay. And the slides should be, where's the mouse? Okay, your slides are right here. Maybe this got disconnected. Here are your slides and Zoom. Do you see Zoom there? No?
No.
Why did that happen? Let's try sharing again. Okay, can you see it now? Can you see it now? Okay, okay. So here the amounts.
Not make it in the presentation.
Yeah, we'll put it into the full screen. Well, it's, no,
Presentation mode.
it is there. Okay, I think it's ready. And use the mouse to navigate.
I think it's not cool. Okay.
See here, I don't know what to do. Yeah, it's good.
Okay.
Does it work?
Should we try to share the screen again?
What?
Applicate
Oh.
there.
Let me try one thing. Let's do it now. Let's do it now. Please go ahead. Please go ahead.
Okay. Can I start?
Yes, please.
Okay. I'm Yusuke Sakami from Chiba Institute of Technology, Japan. First of all, I thank organizers and the committee for giving me opportunity to give this talk. So the presentation title is Physical Modeling Approach for Simple and Energy Efficient Analog Neuromorphic Computers. So I'm a senior researcher at the Chiba Institute of Technology. This university is located around here, next to Tokyo. My research goal is to create an analog silicon human brain. Human brain is a very nice computational element. It shows a variety of functions with only 30 watts. So if I can mimic the same dynamics of the brain, so we can create a human silicon brain, so with very low energy. So this should be suitable for edge systems such as robotics. So I think many people in this workshop are not familiar with analog computing. First, you'd like to overview the AI hardware research. So in conventional computing, people often use artificial neural network or deep learning models. So this model is computed on the digital circuit, such as CPUs and GPUs. This is a standard way of computing AI systems. So recently, analog circuit is attract many attentions for reducing the energy for computing artificial neural networks. This is known as in-memory computing. This is very nice paradigm for the next generation computing. So silicon brains, so uses spiking neural networks instead of artificial neural network. So then this is computed on analog circuit too. So in this talk, we focus on in-memory computing and silicon brains. So this is the overview of my talk. I will first explain the background of my research. So first, in-memory computing for artificial neural networks, and also explain the challenges in in-memory computing circuit design. So then we'll explain the results. I will first build a physical model of in-memory computing circuits, then map that network to the in-memory circuit. So this physical model can be interpreted as a spiking neural network. So finally, we do a circuit simulation using open source and SkyWater 130 processing design kit, PDK. This figure shows the we do. So usually people train artificial neural network, then so map the trained weight to hardware. This is the standard way. So we do the same thing, but I use a spiking neural network. So that's all. So what is in-memory computing? So standard computers have processors and memory. So this architecture is called von Neumann architecture. So this architecture is basically efficient. However, for machine learning applications, so there is a severe energy bottleneck. So this is because the energy consumption by memory access is much larger than energy consumption of computing itself. In-memory computing solves this energy bottleneck by transferring the computational capability from processor to memory. So because of this architecture, so there happens a pure data movement. So this is very energy efficient. But if it's analog computing, you have to deal with analog circuit. This is difficult. However, so the recent survey showed in-memory computing are best in energy efficiency. So this is very important direction. So this slide explains the computational mechanism of the in-memory computing circuit. So there are two types of in-memory computing circuit. So the first one is current-based in-memory circuit. This is a simple circuit. I think you learned this kind of circuit in junior high school. So this is registers, two registers. So if you apply the voltages at this point, so current flows according to Ohm's law, then so according to the Kirchhoff's law, so you can obtain the total current. So the total current is equal to the weighted sum of inputs. So weight is the conductance. So this is why you can compute the deep neural network model with in-memory computing circuit. So another type of in-memory computing circuit is charge-based in-memory computing circuit. In this case, so this circuit also uses resistors, but so it measures the integrated current, in other words, charge, coulombs. So this charge is converted to voltage at the capacitor. Then the input signal is a little different. This is the voltage pulses. Then the final output voltage is equal to the weighted sum of inputs again. So you can also use current source instead of resistors like this one. So in this talk, so we focus on this architecture, the charge-based in-memory computing, because this is more energy efficient. So in-memory computing is very energy efficient, but its design is very difficult because of its analog nature. So in-memory computing circuit have severe process variations. Process variations means the expected characteristic of circuit is not the same as the one of the one you fabricated. So also have no ideal device characteristics, including nonlinear IV, current, voltage, characteristics of VRAM, this is registers, also sleep big current and voltage dependent currents. So in this talk, we focus on this problem because this is one of the major problem in charge-based in-memory computing. So I will explain how the no-ideality affects the dynamics of in-memory computing circuit. This is the in-memory computing circuit. So that uses current source. Current source is the device that produces a preset current I1, I2, I3. So in ideal case, the current of the current source only depends on the process current and spike timing. This is the function. So the time evolution of the voltage, we call this voltage membrane potential. The time evolution of the membrane potential is piecewise linear. And final voltage is weighted sum. And this is the ideal case. However, in real case, the current also depends on the membrane potential. Because of this effect, so the time evolution is nonlinear. RCDK-like time evolution. So therefore, the output voltage is not equal to weighted sum. This leads to loss of accuracy of classification and regression. So this is the proposal. In the traditional approach, so we train artificial neural network, DNNs, so then train this one and you can obtain the weight. So then you map the weight to hardware. However, so in this approach, you cannot take into account in-memory computing non-idealities. So we propose the new approach. So we start from seeing this hardware. So we first build a physical model of the in-memory computing using ordinary differential equations. This can be interpreted as a spiky neural network. So by using the training method of a spiky neural network, you can train this ODE system. Then you can obtain the optimized weight. And then finally, you map the weight to hardware. So this technique so exactly take into account the non-idealities of in-memory computing circuit. So you can model the non-ideality as a spiking neural network with reversal potential. This is the equation of spiking neuron. So we add the reversal potential. So this accounts for the voltage-dependent current. So this have two values. So for positive weight and the negative weight. So you can solve this equation, so then obtain the analytical expression like this one. So you don't have to solve ODEs like using ODE solvers, such as in neural ODEs. So this is easy. You can think this is the activation function of a neuron. However, it is interesting to see the time evolution of the membrane potential depending on the value of membrane potential. So depending on the value of reversal potentials. So when the reversal potential is quite large, for example, 100, the system is almost the same as artificial neural network. So this is the case where the 1000 random input spikes are applied to the neuron. So it shows diverging behavior. So when the reversal potential is very small, like 1, so this reflects the non-ideality of the in-memory computing circuit. So in other words, so this is upper limit of the membrane potential and also the lower limit of membrane potential, -1 to 1. So the membrane potential behavior is different, so a little confined behavior, so also very complex. But we will see that we can train this network. This is the result. We trained the network of fully connected layers on the Passion MNIST dataset. The horizontal axis is reversal potential. So when the reversal potential is very large, the system is ANN-like. So training is very easy and performance is very nice. So however, reversal potential is when reversal potential is very low, because like 1, so there is a very severe nonlinearity. However, so if we take into account this non-ideality in the training phase, so there are few drop of performance, about 0.5%, but only small degradation. Instead, if you train the artificial neural network, so without taking into account no idealities in training phase, then in the test phase, so you test the system with the reversal potential effect. The performance drops rapidly. So this means, so taking into account no idealities, or in this case, reversal potential, is very important in the test training phase. We also trained a large scale neural network, which is BGC7, on CPAR10 dataset. In this case, so we cannot observe any performance degradation. So even reversal potential is very low one. So instead, the performance slightly improved, maybe. So this is surprising for me. So if this is true, so you can intentionally add no ideality to hardware to improve the learning performance, also improve the energy efficiency and dimension efficiency of the circuit. So up till now, we show that by taking into account no ideality as a spike in neural network, so the no ideality is not problematic. We see that this is the same for the real circuit case. So we did the circuit simulation. So we checked the modeling error between the traditional approach and proposed approach. In the proposed approach, so in the traditional approach, so we compared the ANN case and circuit simulation results. In the proposed approach, we compared the SNN results and circuit simulation results. We show that the modeling error for the proposed approach is much smaller than modeling error for the traditional approach. We designed circuit using open source PDK. This is the SkyWater 130 process, and also I used open source software. So these softwares. Then this is the design the circuit. So this circuit is very small. So each layer have only 5 neurons. This is one layer. This is one layer. So this circuit has 2 layers. So each layer have 5 neurons. So then 5. So this is one neuron circuit. And this is one synapse circuit. So when input spike comes, so this synapse circuit converts the input spike into the current. Then, so neuron circuit get this current, then produce a spike to the next layer. And the next layer works as one. So this is the working diagram of this circuit. So each layer have the 3 phases, reset phase, and accumulation phase, and spike generation phase. In the reset phase, so the membrane potential is set to the initial value. In the accumulation phase, so it accepts input spikes, and the membrane potential time evolves. In the spike generation phase, neuron output spikes. This is the synapse circuit. The horizontal green line is for spikes, and vertical line is the dendrite that is connected to the neuron. When spikes come, so this gate becomes open state, then current flows. And so importantly, so this memory has very severe non-ideality. So this figure shows that. So the horizontal axis is the membrane potential. The vertical axis is the current. So usually this is used as a current source. So these lines should be horizontal. But in this case, so we observe the severe inclined line. So this is a severe no ideality. So, however, so we saw that, so by taking into account the no ideality in training phase, this is not problematic. This is the neuron circuit. So there are two components. So in the input component, it just accumulates the input synaptic current and get the charge and get the final membrane potential. In the output component, so convert the final membrane potential into the spike timing. This is the simulation result. This is the simulation result for the ANN to a memory computing circuit mapping case. So first, let's see the hidden layer, and black solid line is the membrane potential. In the reset phase, the membrane potential is set to the initial value. And in the accumulation phase, so it accepts the spikes, then time membrane potential, it changes according to the input spikes. Then finally, in the firing phase, the membrane potential monotonically decreases. Then if it crosses the threshold exists around here, the spikes arises. Spike is the blue solid line, this one. So you want to, we want to see that in the output spikes. So for the model's output spike is vertical dashed line, this one. And the circuit simulation's output spike is vertical blue line. So there is a huge discrepancy. So this shows the DNN to AMC mapping is not working well. Yeah, and as for the proposed case, so you cannot see any discrepancy between the circuit simulation, black vertical line, and sorry, blue vertical line and dashed red line. So this is the result. So we see the standard deviation of the AN model case is 26. However, so for the case of SNN model, it's 2.2 nanosecond. This is much lower than the case lower. So this is a summary. Physical modeling approach allows us to use no ideal devices. We demonstrated this by circuit simulation based on SkyWater 130 process. Thank you very much for listening.
So we have a few minutes for questions, and I already see one question. And I will repeat the questions because of the microphones and recording. So please go ahead. Question.
Yeah. Do these results take into account process variation that might affect T and T?
So the question is if these results take into account process variations and other sources of error.
Yeah, it's a good question. In this case, I did not take into account any variations. So in this case, in this work, we focus on the no ideality only. So the process variation is the next step. Thank you very much.
Any other questions?
So I'm not a hardware expert, but it's really impressive to see the that you are working on analog processing for neural network for artificial intelligence. So the question, so I understood you use spike-based communication with asynchronous communication that you are using. It means you have jitter and latency probably. So did you have an evaluation of what is the data that you can take into your circuits that doesn't hit this level of jitter at least inside circuit?
So the question is about jitter and other sources of error.
Yeah, that is a very nice question. So in this case, the circuit speed is very low, microsecond scale. So however, the spike is digital circuit. So this is very precise. So in this case, we have not observed any jitter errors. Yeah, thank you.
Thank you. I have a question about when you talk about you compare DNN and SNN mapping. I did not really understand what is the exact difference here because you're still talking about size when you talk about BNN, so I was a bit confused, like what in your model is really different between the BNN and SNN?
So the question is about the differences between BNN and SNN model.
Yeah, that is a very good question. So in this talk, so we don't use as pure SNN. So I just modified artificial neurons by taking into account the reversal potential. So I mean the ANN that have the infinity value of reversal potential. So this system is not event driven. So it has two phases. So this is not spiking neural network in exactly speaking.
Yeah, I wasn't aware about this reverse potential thing. I was also on spiking, but we never heard about this reverse potential. But is it something that's invented or is it coming from?
Reversal potentials take into account this no ideal effect of the circuit. So the current changes depending on the membrane potential. This is the same effect of reversal potential. So that's why I added reversal potential term in the neuron. Is it clear? Yeah, thank you very much.
Okay, one final question.
Thank you for the presentation. What are the limits of your the structures of the neural network? I mean, you applied for CNN, but is it applicable to every kind of network? Or what are the physical limits?
The question is about the physical limitations of this approach.
Yeah, this is very important question. So I think the most difficult part of analog circuit design is scalability. So because the almost all neural network, the current neural network have the weight sharing mechanisms. You have to store the output activation for a long time. So this is very difficult for analog circuit. So you sometimes need AD converters, but it consumes a lot of energy. So the architecture for communication and store the output activation is very important. So I think that's the most important for real world implementation.
Okay, thank you for the presentation. Thank you so much. Our first speaker in terms of the papers will be Tewei. He will have the opportunity to test our time policing system. And I would invite the next paper presenter to be prepared to jump in right after Tewei and then the next one again. So let's see. I will have to share the screen again. Close this one. This one. So let me share the screen again. Tewei, are you ready?
Yes.
Okay.
Makinos.
Should be able to see it now. Is it
Yeah.
there? Is it there?
Yes.
Okay. So yeah, we're gonna get through that. Okay, it's your turn, Tewei. It's gonna start in a few seconds.
But
Go ahead. Go ahead.
My name is Zoe Chen. I'm working with Canon. The title of our paper is Dedicated Inference Engine and Binary Weight Neural Networks for Lightweight Instance Segmentation. Many researchers implement binary weight neural network, BNNs, on embedded hardware platforms to reduce the computational cost of image recognition tasks. There are two problems. The first problem is that the hardware cost of the inference engine for BNNs needs to be reduced. And the second problem is that the accuracy decreases when the weights of networks are binarized. So we proposed an inference engine to handle this kind of problems. The contribution of the paper is twofold. So, yeah, the first is that the first new design methodology to reduce the gate count of the inference engine by removing a part of computational cost from the hardware system is proposed. Second, the proposed inference engine can handle instant segmentation algorithms with only 9.8% of computational cost compared with the related works. This is the hardware architecture of the proposed inference engine. It includes a bitwise operation and accumulation array, and the adder array, and the quantization and activation unit. The bitwise operation and accumulation array includes multiple logical operation units, which are shown in this figure. And it can support two kinds of BNN operations, which are shown in the tables below. And a part of computational cost of the first BNN operation can be removed from the system because they are not dependent on activations and can be performed in advance using any other kinds of processors. The inference engine and the BNNs are also compared with related works to show that the proposed inference engine can handle practical applications. Two lightweight binary CNN, binary neural networks are also proposed. The results show that the proposed BNNs have 77.7 smaller model size compared with the related work YOLACT. But it has a higher accuracy than YOLACT on the person category. Also, the experimental results show that the proposed hardware has only 52% of hardware cost compared with the related work, which is a exclusive NOR-based multiplier. Please come to our poster for further information. Thank you.
Okay, next author, please. You're going to start in a few seconds.
Yes, everyone. My name is Carlos Panaguanvest. I am sharing our paper, which likes crude disease detection through pre-simulated Boston quantization. On this paper, we're tackling three issues. The first one is crude disease issues. The second one is deploying model on raw design device. And the third one is to find the optimal way to quantize those models. So the idea here is come to deploy model, we're facing issue of power consumption, memory, IBAN. When it comes to quantization, we need to find what's the best way to reduce quantization error. We are proposing our approach to tackle this issue of quantization errors, what we call pair similarity quantizations. What is the main idea to take away for these issues?
You can go forward, yeah.
I feel I was expecting you to walk it on. So the main idea is to make sure that full precision models, in this case of red blocks, and the green blocks, which is quantized models, to have the pair similarity of activation functions. We believe that if we can do that, we can improve the quantization errors. So we have here outputs for quantization model, red block, green block are quantized, and then we perform the pair similarity here, to find the best way to factor quantization for weights and also activation functions. The green bullets here, we see more detail out what is happening. So we focus on main bits weights quantizations. So with this, we expecting to reduce power consumption, IBAN, and memory consumption. We perform our experiment a wide range of bit weight quantization for 2 bits to 6 bits, and also we try to compare with the other method of existence. We can find out that our approach managed to overcome the others. So here's important highlight that we focus on object detections with many tasks. So come to Boston to get more detail. We hope for improvement. Thank you.
Thank you. The next presenter is going to start in 4 seconds.
Yes, good afternoon, everyone. We are all here because we think that deploying machine learning models on a device, on an embedded device, is a good idea, and I definitely agree. But this also increases the risk of someone else, a third party, obtaining your model. The model is deployed on the device of the user, so the user will have access to the trained weights and might extract it for their own purposes. And this it's probably not an issue if it's an open source model, but we are increasingly seeing applications where a company has invested a lot of money in gathering training data, cleaning the training data, training the model. And so a trained model can represent a significant intellectual value for a company. And then just deploying the model on a device is risky, and a lot of companies are hesitant to do that. And to do that, to solve this, we need some kind of protection mechanism. And there's a lot of recent work on watermarking of deep neural networks. It's a weak protection. It does not solve all potential attack vectors, but it's a very cost-effective way of providing some protection. And especially important is that it has no runtime overhead. So that's very important for embedded applications. So watermarking embeds some kind of identification into the trained weights of a model. There are a lot of algorithms to do this, but crucially, existing algorithms take a lot of time to generate a watermarked version. So what we propose is a very fast, efficient way to generate a large set of different watermarked instances. All of these watermarked models behave in the same way, have the same or very similar accuracy, but they behave differently when prompted with certain key inputs. And these are inputs that are used to extract the watermark. And that way, if your model is stolen, you can prove that it was indeed your model that was stolen, and you can trace it back to the user that originally, where the model was originally sent to. So if you want to learn more about watermarking and how we do this, please come talk to me at our poster. Thank you.
Excellent, thank you. Wow, the time police system works really well. Okay, our next speaker is Zoran Kostic. It's also an invited talk, and we are doing great with time. So let me change the PowerPoint. Lost this. Okay. Did we lose the connection again by any chance? Can you see the screen? You see it? Okay. Zoran, please take it away. You have 20 minutes. I'll remind you if needed.
Thank you. So I'll be talking about the system, but we're building a system which we want to behave as an embedded vision device. I'm going to introduce you to what it is and how we would like to accomplish that and what kind of problems we have in getting to that point. And I'm speaking to the microphone from now on. So many students are involved in it and a bunch of faculty. This is done within the auspices of an engineering research center at Columbia University called Smart Streetscapes. And we have all of this technology, cameras, networking, high-speed computing, all sorts of things. The reason why NSF gave us money is to figure out, can we use this technology for some social benefit? So I'll tell you where this is going and what technological pieces of the story I'm interested in personally. Lots of collaborators. The main collaborators right now is Florida Atlantic State University, Rutgers, University of Central Florida, and Lehman College, which is part of City College, bunch of companies, and so on. So the application focus areas. I'll read the bottom here: road safety and traffic efficiency, public safety, assistive technology for handicapped individuals, the future of outdoor work, and what we call hyper-local environments. This center started about a year and a half ago based on a testbed that I'll talk about, but these are the pilot applications. Something that's called StreetNav, essentially wayfinding for visually impaired individuals. So it's a very sophisticated method to precisely let people who are visually impaired have advantage over other participants in the traffic. The second one is smart intersections. I'll talk about that essentially in this particular talk. And the last one is what we call municipal mobility intelligence. For all of these applications, privacy and security are super important. I'm not paying attention to that right now, but cannot be forgotten. So we run 3 testbeds. The first testbed is called Cosmos testbed. It is deployed in New York City, in Manhattan, in Harlem area, close to Columbia University. The second one is deployed at Rutgers University in New Brunswick, New Jersey. And the last one is in West Palm Beach, Florida, called Mobility Intelligence. They have been designed with different goals initially, but whatever we run at one test bed, we're now trying to replicate in other test beds as well. So the idea for this came out of evolved from something that exists for about dozen years, right? A little bit more. What you are looking at here is in a large, I guess, room, let's call it a room, with about 400 nodes at about 1.5 meters squares. Each of these nodes has any possible wireless technology that can exist, Wi-Fi, Bluetooth, version of cellular, and so on. This is more than an emulator. This is an engine for running simulations for indoor wireless and doing all sorts of other interesting things. DARPA competitions were run there and so on. So the idea was, okay, this is an indoor thing. Can we build the same thing outdoor? So Cosmos is this name that we gave for the outdoor testbed, essentially deployed in the surroundings of Columbia University. What we're looking at here, to the left is south, to the right is north. This is Manhattan. This is the boundaries of Columbia University. This is Columbia University. This is City College of New York. Every of these square blocks is a node. So this Cosmos project originally was about building nodes, sophisticated radio nodes, with software-defined radios for experimentation for radio purposes, wireless communications purposes. But you can imagine if you deploy that, what are the applications that we can build on top of it? So that's what I focused on more so than radio aspects, which meant that whenever a new node will get deployed, I would stick a camera onto it. Although we were not funded for that initially. So there comes vision. And we'll get to the embedded vision in a few moments. So this Cosmos testbed, it's not only about the radio node, it's also about the whole infrastructure. So it's a very high-speed optical, ultra high bandwidth communications. So each radio node does have access to it, as well as high-end computing devices. So we call that an edge cloud. But since our network is private for communications purposes, this optical network can run as far as 40 kilometers or whatever, 30 miles away in New Jersey, at Rutgers University, and still have super low latency, which is really important for what we're interested in, for real-time applications. So I'm a communications engineer. For me, every millisecond matters a lot. So I've gotten used to power control bits that have to come, essentially half a millisecond after I've requested them. Now, in applications like this, it's not easy to get very low latencies. So the ambition is, you'll see in a couple of seconds, can we build parts of the system to have really, really low latencies? And if you have a problem with, where are we going to take it? Anyway, this network, the application domain, because of ultra low latency and edge computing capabilities, anything AI. So we have high-end A100s and B100s, now H200s for AI stuff on the edge cloud. We have very low-end devices such as NVIDIA Jetson Nano in the realm of low-end GPUs. So a variety of applications. This is the location of the pilot site of the Cosmos testbed. This is Amsterdam Avenue. This is 120th Street. This is the MUD building, engine building. And this is where I've deployed at least 4 cameras, 2 on the 12th floor, 2 on the 1st and 2nd floor, to play around with. To do what? So I'll almost skip this, but I'll tell you that, as you can imagine, so the large nodes are actually very, very high-end cellular nodes. These are $500,000 deployments with large software-defined radios and several kilometers range. We build that actually. This is custom hardware. Then we have medium nodes. This is the outside of the medium node. On top of this, you have antennas. At the bottom, you have a camera. Behind this is a panel that looks like a large electrical panel in a residential house in the United States. And then we have portable nodes. But a large number of software-defined radios, edge servers. This is more than 20. We have probably 4 dozen right now. These are routers, optical routers, and about 40 miles of dark fiber. So the dark fiber was important because we didn't want to compete for traffic. For experimentation purposes, we didn't want to compete with anybody else's traffic. We zoom in into this pilot intersection. We call it the Cosmos pilot site. 2 cameras on the 12th floor, 2 cameras in the 1st and 2nd floor.
And they're connected to this private network, to the computer room here, as well as 50 miles away, New Jersey, 8 miles away at New York University. So an interesting problem. At universities such as Columbia, running a video stream off of the first and second floor camera is really, really hard because of what's called IRB, Institutional Review Board. It's almost like you want to have a consent from everybody who passes by that camera. So lots of the research of this type is limited by that aspect, but you have to deal with it. So most of the time I dealt for the beginning with the 12-floor cameras, the tiny little pedestrians and a little bit bigger cars. Then all of these neural networks models that you get off the shelf really don't work, so you have to fine-tune that to a significant degree. So there's an argument here. If you have Manhattan type of environment, you have very complex traffic environments. So I would dare to say that the way that autonomous vehicles work today may not actually work in situations like this. So you have these 17 yellow cars and the unruly behavior of pedestrians. I mean, they're probably going to get stuck. So one of the premises here, we need some contextual awareness, situation. Is there something that can capture the whole situation? And can it be shared with everybody who participates in this traffic? So one way of addressing that is just having a view at the whole scene, being able to capture, detect, and track every vehicle, every pedestrian, and share that in some meta format in wireless broadcast type of mode to everybody there. So that's like the goal. That's where we're going. The real problem is, when is that useful? Okay, you can do it, but when is that useful? So you have to think about real time. A couple of more pieces of information. The other thing that you can do, we're not there yet, we can also harvest the content of sensors that are in the vehicles. So their cameras, their LiDARs, harvest it in, have our own cameras, combine all of that and see how far we get in terms of precision of location. Okay, so city infrastructure, the exchange of data between vehicles, harvesting the data from vehicles. To support all of that, you do need a network and the testbed such as Cosmos is. So we can actually do all of this. We are in the sort of technical mode, technological mode that we can do that. So we can consider one of these nodes as a reasonable center of intelligence for this intersection and the surrounding sensors and the connection to the network, to the computing device is good enough. So there comes a question that many people ask. So if I want to have very low latency and I have a camera here, why don't I just put the GPU right there? So there, if I need an interaction with the environment, that's going to be very close by, and closing the loop, that's going to work. Yes, but sometimes you need to want to have some sort of collaborative work between multiple of these sensors, in which case you may actually prefer to have a large GPU somewhere in the edge cloud, but not lose not suffer from the latencies that you have to experience because you have some communication link and something in between the sensor and your computing device. So anyway, this is just a low-end GPU, NVIDIA Jetson, a high-end GPU, Ampere. So that's a trade, you have to balance between these things. As a matter of fact, it's quite likely that sometimes you want to run it in this mode, just using this GPU and close the loop there. Sometimes you want to close the loop up here. But what do we have to do? So I've been torturing my students with, what do we have to do such that we can push whatever data we have at whatever rate it is and not suffer from the latencies that are implicitly in these links. So that's like, okay, I'm trying to build a system that almost behaves like an embedded device, although it has all of these links. That's what the essence of this work is. If you worked with these devices such as NVIDIA Jetson Nano, these are Linux computers with very capable GPUs, but for very small amounts of memory, they can run these AI models like what is called YOLO, you only look once and so on, reasonably well. But if you have high resolutions or you have if you have needs for improved or better performance models, you may have to actually go to some more capable device, which is not in Jetson Nano. So every aspect of this thing has to be looked into to judge what can you do and how do you make a flow of the data all the way from the camera to whatever the device is. NVIDIA is paying a lot of attention to optimizing the processes and software stacks, and there is something called Deep Stream Pipeline, which works pretty well, but still may have a little bit of weight that is not serving the purposes that I would like to go to think about this as almost like an embedded device. There's still delays there. So I conjured a target application. I said previously, I'll call it a radar map. So I'll show you in a second what the radar map is. We have cameras, they look and they detect and track objects. So we also harvest the data from these objects, maybe cars, their sensors as well. And whatever magic we do in the artificial intelligence and so on, we want to compose a radar map for full contextual information, like looking from above at the whole scene. And we want to broadcast that map in some wireless format, in a meta format, back to cars and so on. And this would be we want to do that in real time. Now, the problem is, what is real time? Every community, technical community may have different ideas about real time. I'll tell you what my idea about real time for this application is. But we want to close the loop. Observation, processing, go back, inform everybody about what you observed. So we'll run a tiny little video. Okay, how many minutes do I have?
You have 6 more minutes.
Excellent. So what you're looking at the bottom here, we'll see if the wireless connection works. If it doesn't, we'll just skip it. So I'm going to skip it. Down here you have a video, and you have vehicles moving, and pedestrians and bicycles. And let's consider this to be I'm going to call it a radar map. These things are going to be moving. These are vectors of motion for vehicles, pedestrians, and bicycles. Imagine we can get that very reliably with high accuracy, whatever models we run, and we just want to broadcast that to every single autonomous vehicle that is in that intersection. They can do whatever they like with it. Is that right? It's just some sort of meta format, but they gain contextual awareness of the scene. Now, if that were to be useful, we have to agree on what is real time. So I'm going to talk about real time. Before I open the next slide, I'm going to remember some things. So 3 times 10 to the 8 is the speed of light. Is that right? A vehicle in the intersection, think 10 kilometers per hour, pretty slow. But that is equal to 3 meters per second. Now, if I spend 1 second on closing some processing loop, a vehicle moves for 3 meters. That's actually quite a lot. You're going to hit somebody, you're going to have an accident or whatever. If you have high ambitions and say, I want to create sort of a closed loop system, well, I'd like to act within 10 centimeters, maybe. Is that right? That's maybe useful. So 10 centimeters means that I would have to have a loop closed at 1 second divided by 30. In 33 milliseconds, I would have to close the loop. Observe, process, and provide the feedback. That's actually a very tall order for systems that have networking in itself. But let's try to break it down. This just shows you what I've been talking about. Essentially, the target for this application could be, is there a way to close the loop within 33.3 milliseconds? Or what would we have to do? Today, can it be done? Or what do we have to do to be able to do it? So what contributes to real-time consumption? You start with sensors, cameras, just the sensing takes a long time. Video encoding, if you're using a video compression, RTP, RTSP streaming. Communications, have infrastructure that they have to cross, switching, protocols, routers, and data processing, whatever that means, detection and tracking in AI or some sort of intelligence behind that. The goal, again, is getting some contextual awareness. The fact is that even just a very frequently used image sensor by Sony, it takes about 10 milliseconds to capture just the sensor data. That's actually quite a lot of time, is that right? My goal is for the whole loop 33 milliseconds. Immediately, I think this 10 milliseconds. Very, very important to be aware of. Those of us who have some understanding of video compression, the practicality of video compression, it's a great thing. Something that would otherwise take 1.5 gigabits per second to transmit raw data for HD type of resolution. So I had 1.5 gigabits per second to run at 30 frames per second. If I do video compression on average, that's only 12 megabits per second. That's why video compression exists. However, if you get off-the-shelf cameras, when vendors implement that, you have zero control over the buffers. And how do they buffer the video encoding? So you may immediately run into 100 milliseconds of buffers if you just buy this camera. So you can't rely on that. You have to build your own system, attach some camera, get the raw video feed, and probably, it seems that maybe we are not going to want to use video compression because these buffers are quickly accumulating. When you have a buffer, you have a delay. So that's another piece of the story we're investigating. What do we have to do if we figured out that the compression sort of doesn't work because of the delays? Now, one thing that I said, we have super high bandwidth optical communications, parallel communication network in hundreds of gigabits per second. So now I'm making an assumption, which is actually verifiable. I don't care if I had to transmit 1.5 gigabits per second raw data. That's fine with me. I can do that. But as long as I figure out a methodology where I can quickly shoot these bits from the device that's collecting the data to the device that's computing. I don't want to do video compression. And you will figure out quickly, I actually don't want to do video streaming as it's done with RTP, RTSP, because that's another thing I don't have control. These RTP real-time protocol, real-time streaming protocols, they will take a lot of time to warm up and to do what they need to do. So we've done, and I say, to my students, we go through these steps. Let's measure everything. What's the delay? How much delay? Do we know what to do about delay? Yes, indeed, you quickly figure out that whatever you can get off the shelf very quickly eats your budget. This is 100 milliseconds. Is that right? Whatever the exact example is right here. So I can't really use it. And we've done a variety of studies. Even if you use this Jetson, this is Jetson, NVIDIA Jetson, one of the versions of them, the so-called Orin, even the stack, software stack that's written for that, a very sophisticated, good stack. However, even that stack is sort of too slow for what we like to do. So you have to custom code, sort of create state machines that don't deal with operating system, with Linux and so on. You just want to shoot bits out, suck in the bits from the camera and shoot them out. This is a little bit about the variability. Let's try things. Let's change the data format from float A16 to UINT 8, do you save something? Don't you save something? That's actually the relatively minor changes in the number of bits that you have to transmit. Doesn't help enough. The other thing that is very frequently forgotten, if you read research papers on the inference on AI, people do report how models work fast. But my impression, my conclusion is that they mostly think just about the inference, just strictly the inference in compute node. However, if I were to show you exactly what this is, green is the video pre-processing, the blue is actual inference, and the red is some post-processing. 70 or 80% of time, I'm not doing the inferencing. I'm preparing my data to do something. That's what needs the time. So that's an important thing to have on your mind if you're trying to deploy a practical system. Again, some measurements like this, what is called the tiny YOLO system, and this is 2021, 2022. This says it's running at 47 frames per second. That's faster than real time. 30 frames per second would be real time. So it's okay. Just inferencing is good. It's fast enough. The stuff around it is slow. Transmission over the network and video pre-processing and post-processing.
Time for questions.
Yeah. So let's just do the following. I'm going to say that so the customization of this thing goes in the direction where we say we have to custom design the protocol. We have to shoot raw bits, and we're going to do that in our work. And that's where I'm going to end. So this is the system. Parts of the system we'd like to behave almost like as an embedded vision device. Thank you.
We'll have a few minutes for questions.
What about skew between cameras?
That's an exceptionally important problem. So the putting timestamps that let you measure the latencies and making sure that all the devices are synchronized it's quite an issue. So these protocols such as PPP and so on that you have to run to synchronize the devices. But again, each of these devices most likely has to be a Linux computer to do that.
you have to do that synchronization.
Real world inference time is a function of complexity of the scene. The dynamic of the scene by itself. How do you do that?
So we've done studies on that aspect. It is indeed true. But I have to say the variability for the dynamics of the scene. So in our example, we have many cars and many pedestrians, or an empty intersection. You imply that you think, I mean, it's not the dominating factor here. The latencies that we really deal with are in completely different domain. It's really over the networking pieces of the story, rather than this. What I'm saying is that somewhat less second degree to the problem that we really have.
Thank you. Pre and post processing, and I think what you said, you said the red is the post processing.
So the green is post processing in this case. The red is pre processing in this case. Yeah. I mean, the exact numbers sort of don't matter. The relationship between inference versus the rest.
You have an example?
So imagine you're doing this deep variety of frameworks exist for passing the data from detection to tracking to some sort of intelligence. And in between those steps is where you have sort of post-processing losses.
So in a sense, you've been showing two extremes, let's say, on the design spectrum, right? On the system design, do everything locally, quick, do everything in the cloud focus on network, right? How do you think about the middle, right? Or more precisely, meeting exactly the requirements that you need?
Yeah. So the way I'm thinking about what you're referring to is more like sometimes they'll do this and sometimes they'll do the other. It seems to me that I don't see the middle ground. I mean, this is hard enough. If I just at this moment, I just want to figure out, can we actually do it remotely with these such low latencies? You know, how much an effort that is? And I know one thing, with all the shell stuff, we cannot.
That's the last question. Go ahead.
There is specific reason that you use GPUs for processing. And if the latency is a problem for you, so GPU maybe is not most trustworthy for you. It provides you flexibility, but
So if you say, I just want to do the network type of stuff, I don't have to have a GPU in between. You're correct. I don't have to use I don't need the Linux computer or not even a Linux computer, just quickly shooting the bits. So you're absolutely correct. For me, it is convenient to use something like NVIDIA. It is Linux computer. I can do their stuff, but I can also do stuff elsewhere. But the fact that initially NVIDIA didn't design their systems with watchdogs, that they're very careful about driving the interrupts is the problem. So there are better devices for embedded computation.
Let's thank our speaker. It will be by Lucas. Let me make sure we fill this down.
I'm presenting with my laptop, so I need to join the Zoom so you can record when I present.
Yeah.
And you have the information of the Zoom?
Yes, ready?
Send it to you.
Okay, it's gonna start in 4 seconds.
All right. Good afternoon, everybody. My name is Lukas Flickenstein, and today I'm happy to present collaborative work pruning as a binarization technique. And CNNs have shown to be effective for many computer vision applications. However, at the cost of employing more and more complex CNNs. This made it difficult to meet hardware execution budgets, especially in hardware embedded devices, and leading to an increased interest and attention in network compression techniques. For example, pruning removes entire structure from the CNN computation graph, while quantization reduces the bit width of the network operands. An extreme form of quantization are binary neural networks, where early works have shown compelling efficiency benefits, although with a sizable accuracy gap compared to their full precision counterparts. To this end, we present a novel compression technique which leverages pruning as binarization technique. Many works in the domain have explored multiple remedies to improve the prediction capabilities of BNNs, which can be classified in 3 parts. Some works on gradient approximation techniques aim to solve the problem of restricted gradient flows caused by discrete operations in the BNN when training with standard optimizers. Some other works introduce scaling factors or scaling factor formulations to minimize the reconstruction error between the real valued parameters and the binary counterparts. And then there are other studies that investigate different network architectures that favor the binarization process, such as multiple skip connections. Although many works in the field have improved the prediction capabilities of BNNs, we in our work present a new viewpoint to achieve high accuracy BNNs. For this, we use multi-bit networks where MBNs decompose standard convolutions into multiple binary convolutions. Thus, MBNs encode the network parameters as a weighted sum of binary bases, and where the bit width of the particular parameter that we're talking about is equal to the number of bases that we are using it for. So therefore, our work used pruning an individual binary base in an MBN as a reduction of the bit width of its operands, meaning quantization. So when we remove and prune all binary convolutions of a particular binary base, pruning collapses into quantization. And with this, I'm referring to the poster session upstairs, slide number, poster number 62. Thank you.
Hi everyone, I'm Manon Damphofas. I'm from the University of Grenoble-Alpes in France. So today I'm going to talk about event cameras. So I don't know if you know about it. Contrary to RGB cameras, where you have at each frame a full image acquisition, event cameras, they are event-based, so it's asynchronous. So each pixel has its intensity threshold, and when there is a change in light intensity that is detected, it produces an event, which gives this kind of point cloud data, which is very high temporal resolution in the order of microsecond, which is very good to detect fast motion. And then also spiking neural network, which is bio-inspired neural networks where the activations are spiked, so they can be also seen as events and processed input asynchronously on event-based hardware, such as neuromorphic hardware. So the task I want to solve is lip reading. So this is the task of reading on the lips just with the visual input. And here I do it with the event camera. So this gives these raw events that I can directly feed to my spiking neural network. So the idea is to have end-to-end spiking processing, but then I can make event-based, and so I can have a high energy efficiency. So my SNN is composed of spiking CNN and then a spiking weighted reference unit for the temporal modeling.
You can move it forward if you want to.
So the idea is that not only we reach state-of-the-art accuracy on this task, but more importantly, what we show is that we can highly reduce the number of operations per second by using a spiking neural network rather than a standard artificial neural network, actually here up to by 22. And this is due to the high spike sparsity due to the use of events. And this decreasing number of operations, it can lead to very high dynamic energy consumption savings in when it is implemented on neuromorphic hardware. So please come to see my poster to discuss more about it. And thank you for your attention.
Thank you.
Hello everyone, I'm Cevahir from Aselsan, which is the biggest security company in Turkey, and I'm happy here to present my work on efficient video stabilization with partial block phase correlation on edge GPUs. So the scope is actually all the cameras are clever nowadays with their AI capabilities, but pre-processing is important to provide the efficiency and to get the algorithms have good results on the running times. And so there are, since they are on the edge, they have limited computational source, and your preprocessing should be as fast as possible. And there are different alternatives for stabilization, phase correlation, tracking, and neural networks. But I mean, we in our study we compare them and we come up with phase correlation. It's actually based on partial block selection. We use some GPU implementations and decide the blocks to be used for stabilization. After doing some phase correlation for selected blocks, we merge them in a weighted manner, and then we find the shifts on the cameras and provide the frame corrections and enable stabilization. Actually, we have GPU implementation in detail, and in the end, we double the frame per second capabilities compared to the state of the art on Jetson Nano chips that also mentioned previously, and we have almost 150 frame per second capability for stabilization, and we save enough computational capability for the additional processes on the device. So for more details, I want to come to my question. Thank you.
Yes. Thank you so much. We are doing great with time. Our next speaker is Mario Munich from Embodied, and he will use his own laptop. So let's try to do this. Let's try to do this.
Good. Yes. Okay. Almost working. Okay. So my name is Mario Munich. I'm from Embodied, and I'm going to be talking about Moxie. And Moxie is a robot for interacting with children. I'll do a very brief background about myself. I was a computer vision researcher like many years ago. My first CVPR was in Seattle 30 years ago. It does show how old I am. I work at the company that was called Evolution Robotics. We have a robot that cleaned the floor, and then the company was acquired at iRobot, and I helped build the technology, the intelligence for all these devices. What the key element that I want to highlight here is that I was building devices with real-time vision for consumers. And there is one element that we need to do.
Hey,
when
Mario,
we- yes.
could we ask you to try to share again? Unshare and share again. There is some kind of technical thing.
Sorry. Share.
White one.
The one.
That's one, yeah.
That's better. Thank you.
Thank you.
As in like starting a presentation and then you cut off to throw you off your game. So I was saying that I had to learn by heart building robots for consumer or building devices for consumer. And consumer, and one of them are very price constrained or cheap, if we want to call it simpler. So let's do one exercise. And then this, I learned it on the job. Let's say that you want to build a robot that navigates, it's intelligent. There is a rule of thumb in building consumer devices. Your production cost needs to be 20 to 30% of the retail price. So if your retail price is $300, you have a production cost between 60 to 100, and you need to put everything there. This is a picture of the Roomba 980 disassembled. Everything needs to be in $60. Sometimes, and nowadays, you also need to add the cost of the cloud computing. So sometimes, when I see devices with several NVIDIA, Jetson or whatever, we cannot afford it. We are not going to be able to sell it to anybody. With this premise, let's try to talk about Moxie. So what is the problem that we are trying to solve? We are connected, a lot of connection, but we feel isolated. There are reports from the Surgeon General. There is no people to take care of our most vulnerable, children and elderly. There is a labor gap, and it's very expensive. We would like to have humans take care of humans, but we don't have enough, or the job is very challenging. So we want to build robots that will take care of humans, but they need to be done with empathy. So this is where we come with the idea of the AI companion, and it needs to be a lifelike, believable device that has intelligence. But one type of intelligence is very important is the emotional intelligence. This will introduce robots in our daily life, and they will help with everything. And this is a pictorial this depiction from DALL-E of what will be our life in the future. One thing that the robots have is that they are infinitely patient, empathetic, and they have a lot of knowledge, or they have access to a lot of knowledge. So this is the premise. So let's say that we have to build this robot. What do we need to have as a feature? It needs to have emotional awareness. So you need to look at the user, understand the emotion, figure out what it is in the room and what it's saying. It needs to have a character. It needs to present itself as a device that has the magic of being alive. It needs to have a lot of knowledge that is general, that comes from the LLM or device or context dependent. You can have this robot in a hospital or a school. And meanwhile, all of this needs to be done with privacy in mind and avoiding to be hacked. So the problem is simple, couple of line of codes. So we have Moxie, that's our first AI companion, and I'm going to play a little bit of a video. And the video doesn't have audio, so I'm going to skip it. I didn't try the video. So let's look at what we come up with hardware. And one other thing that I wanted to mention was that the company involved is a startup, and we are trying to create a new device in a completely new environment, a new field. So we don't have anybody to copy. Everything is open. That's a beauty. Everything is open. That's nerve-wracking. Everything is open. You don't know exactly what is going to work. So you go through many stages, and you end up with this picture. It's a robot that is like this, and it's fully packed. It has no room spare. Everything is there. We put there 4 microphones to be able to detect the speaker and to actually zoom in the user. We have a camera. We have a display that is curved. So we want to show 3-dimensionality. We are accustomed to seeing flat screen, but we are not flat. We have 3D and give us a different aspect of communication. We have a speaker, we have motors so that it can actuate. And once we start assembling and figuring out how much we can compute on site, we have, this type of processing power where we spend about $65 in all the Android system. We have the control, it's another $10. And we need a projector to project the face. The face is very important because we convey a lot of information in a non-verbal manner. It's a lot more information being conveyed in non-verbal and with gestures than what you say in words. So if you add them up, we are almost at $200 for 150 plus change. And I haven't started to put batteries and camera, and so it's a big budget. If we do the 3 to 5x, then we ended up into the high hundreds to thousands, and that complicates selling the device. So the other thing is we make trade-off. We $65 for an Android device. And actually, one thing is I had to do an Android device or an Android processor that runs Android because I need to manage the projector and I need to present the face. And in order to animate the face, I need to run Unity. So I start from Linux, Android, Unity, and these are all dollars because this is all memory and computation that I'm spending somewhat. And I cannot spend into running a neural network like YOLO or whatever to detect where people are in the room. So we have a hybrid architecture, and this is a big schema, simplified, which the main inputs are audio and video, and we process part on the robot and part on the cloud. We try to trade off or optimize cost of the device and cost of the usage. The latency, when Soran was talking about latency is so important. When you are talking to somebody, if this person doesn't show anything, it doesn't display a reaction, you kill the conversation. Performance of what you are able to do, detect and extract, and then privacy. The worst thing that could happen for us, we are talking about children, if images of the children appear somewhere on the internet. So how can we prevent that? So we do this with privacy at the beginning. Privacy is center for us. So one of the elements that we did, and here I have a split in three main boards. There is one extra board that I added. It's a processor that is using conference room that does echo cancellation, beamforming, and direction of arrival. I had to spend $5 to $10 there, but it's that much that I can do with a small team. I have the Android board and then the control board at the bottom. This is a simplified version of what I do in the cloud. What are the processing in the cloud? Where one key element that I want to highlight is the safety filters. If you look at the LLMs and you start talking to the LLMs, and you can go into really dark rooms in the world, because these were trained with many different people talking from anything and everywhere. So you need to, if this LLM is going to talk to children, you need to make sure that they're safe, that nobody can curse them, and there is no inconvenient words going out from them. So this filter needs to be very strict. Then I have, how do I do the processing? And this is the processing that is done in the robot. I have a multimodal input. I have the processing in the audio board. I have echo cancellation. I don't want the robot to hear itself. Otherwise, it will be crazy responding to itself. I need to do beamforming, trying to figure out who is speaking. And in real life, when you have a robot talking to a children, you have the mom talking on the phone, you have the TV, you have the sibling. It's a real mess when you hear the sound And we only hear that with beta testers. We don't hear with real customers. But it's very difficult for humans to detect what is being said or who said what. So imagine for a robot. Then we need to figure out where is the voice coming from. Once we have the piece of speech that we think that is somewhat what we need to understand, the robot has motors and they're moving and they're creating sound. And sometimes the sound just in front of where you have the user. So we need to eliminate that. So we need to just cut the piece of speech. When we do that, we do voice ID, we do emotion detection, we send it to the ASR, transcribe, and we eliminate it. That's the pipeline of audio. And this is coming all the time. This real time as it could be. Then we have the image pipeline in which we need to detect the user. We need to track them, recognize them, and detection and tracking, we do it at 10 frames per second. The recognition, we don't have budget, is 1 frame per second. We do emotion detection when it smiles or the user smiles and so on. And then we eliminate the video. The images never leave the robot for privacy. Then we fuse everything. Once we really know that this transcript is from the user, we send it out to the LLM. And there are color-coded different boards. A lot of the processing, as you can see, is in the pink boxes that are in the Android board. So this needs to be optimized, and this is the embedded part. This is why the work is so interesting from the embedded point of view. How do you try to figure out which elements you put on the embedded processor and what type of processor do you select? Without audio, this is not going to be as fun. Oh. But this is a video of myself talking in front of the robot. As you can see, you have a few windows. This window is the real life video that is coming to the robot. I have here the direction of arrival. You can see it's very noisy. So I could be in a cone that is very large. This is coming from the face recognition. And then this is the fusion. Let's say, well, I think that the person is here. Oh, sorry. There are some words that are coming here. These are words that the robot speaks. So these are eliminated from the transcript. Otherwise, the robot will speak to itself. So too bad that we don't have the sound. I have prepared, good conversation about Messi and, playing soccer.
I think that you share it with sound. You didn't share it with sound. You can, when you share the screen, there is a click on sound to share it.
Oh.
But I don't know if you have. Yeah, I think sharing.
Try to unshare and share again.
You have something about sound. Share sound, yeah.
On the right, you share sound.
Yes.
Okay. Let's see. Okay. Well, continue. Sorry. So once we have the information coming from the LLM that is telling us this is what we need to say, then it comes the output from the robot. We get text and emotions, and we have a text-to-speech that is embedded that goes to the speaker. There is a facial animation in the display, and there is also a body animation. All of this is run by Unity. And here is a video in which a video that will pause me. you can see the set of emotions, how the eyes are moving, character feel alive when we show it. There is also very important to have the voice sims to do voice synchronization with the mouth, that it is actually clear for the user. Users are very keen on trying to see what the robot is saying and understanding whether it is actually a fake or not. Like the old times when people will go to concert and will do voiceover and it will not sing. And all the different aspects of the animation that give us time, because we need to go up, we need to get the NLP feedback, and this takes probably 1 to 2 seconds. And this kills the communication if the robot doesn't make anything and signal that is listening. So the last portion of the system, and this is new for me that I'm an engineer, I used to do robot that vacuum, and they have one purpose. They go around everywhere and they clean the room. But now I need to have an interaction. And the interaction means that needs to be a purpose, there needs to be content. So we need to have a whole set of team, a whole other different team that will create this experience with audio, visual, sound effects. And these are some of the activities that we create for children, where we have mindfulness, we have academic activities, creative activities, and this will make the robot actually be enjoyable for users. Otherwise, if we don't have this, it will be just an expensive paperweight. And on top of all of that, we need to build it. And we need to build it for the tens of thousands, of hundreds of thousands, and it needs to be consistent. Robot after robot, you don't want to have a call, oh, this robot doesn't work the battery, the microphone don't work here or there. So these are images from the factory in China, where we build robots, a lot of them. And this is I also had to learn it by my work. It's a different mindset. You build one prototype, great, or 5 prototypes. You need to build 10,000. You better think about it. You don't want to have headaches. So this is a quote from a person that bought Moxie, and with that will be the end of my talk.
Thank you, Mario. Great talk. We do have time for questions.
Thank you. It's very nice. Just wonder, is there any feedback mechanism between the audio and the video processing? Because if you are talking to a recognized person, you know that where the voice will come from. So do you provide a feedback to be informed?
We wish that we could, because since I have an audio processor that is sort of dumb, the current one that we have, it's difficult to actually indicate where you should look for. But yes, that would be the most obvious way of doing it. Or if you had more time to develop, you put everything on a single processor. You could have this dollar that you spent on this audio processor into a better Qualcomm processor or some of the chip that you like with a better DSP. But that's a good question.
Yeah, it is very, very interesting what you are doing, really very interesting. So I was just thinking, if I know you are restricted with the budget, very, very tough thing. But there's something coming, or something high called active learning. Don't know if you know about it. So, for instance, you can embed in the robots learning mechanism like foundation models that can be domesticated. When you sell a robot to a person, it can domesticate to this family. It can actively learn and self-adapt to this habit and so on. And then have a robot that will be having different behaviors in different areas and so on. I know it's very expensive thinking, but are you thinking about this active learning purpose for robotics? Which is
But we call it, I understand and I follow your technical designation. We call it the personalization. We basically, what we have access on a person by person basis are the transcript. So we know what the robot said, what the person said, and from there you can collect what are the likes and dislikes of the person. What are in some of the activities that are academic activities, you can understand how good this user is in math or language, and then change the behavior of the robot or the activities. Try to improve these activities where the user needs help, or try to refresh some of these elements. There is also the input that is coming from an app that the parents have, where they track the progress of the user, and they can indicate, well, we are going on a tough time, so please talk about how the emotions, how is the user feeling. And it's amazing how people or children open up sometimes to a device a lot more than to their parents. And through our beta program, in which we can see how things work, because otherwise you are completely blind. You only see the transcription and you don't know what happened in the real interaction. We see that children get very accustomed and start talking and start just sharing a lot of information with the robot, a lot more and in more natural way that you would have expected. They understand the robot to be their friend, that this is our goal, but to achieve our goal sometimes it's difficult.
Let's do one last question.
Okay, thank you for this. I want to know, you used the 4 microphone.
Yes.
Is it enough to know the position of each
Yes.
person?
Yeah, you have it in the 360. With 2, you can get 180.
And the distance, it doesn't matter if it's in 4 meters or 10 meters, can now.
The distance, it's a problem because the sound will be attenuated and you will not hear it. You can also estimate somewhat with the distance with the camera, depending on the number of pixels. We were cheap, we didn't calibrate the camera, so we don't have the full matrix to estimate the depth. We'll do it in the next version, but it's important also to track, because imagine a scene like this, you have a bunch of faces, which one do you pay attention to?
Okay, thank you. Let's thank our speaker. So we move to 4E for our first poster session. Please be back before 3:40. We'll start sharp, 3:40 sharp. The time police is here. And for those of you online, we're taking a break and going to the poster room, and we'll continue at 3:40 Pacific time in about, 30 minutes or so. Time police.
okay. Yeah, that'd be great. That's good.
So, do you see that? Can you record?
Yes.
Do I need to change anything? Do you see the full screen?
Yes,
Okay,
no problem.
so I think we can get started and hopefully people will come back really soon. And scale this. Maybe give everybody another minute.
Yeah. It was a long way to get to the program. It's minute each, so it's.
Oh, you measured the time?
Yeah, just for a coffee, you cannot.
Oh, you got me the coffee?
Sorry.
Thank you so much.
You want one?
No, I'm good. Thank you. I'm good. Let's start. It's a great pleasure to welcome Marilyn Wolf back to this workshop. She is one of the original organizers of the first Embedded Vision workshop a few years ago. And please take it away here.
Thank you. Here we go. Thank you so much, Branislav, for that nice introduction. So, when we use embedded computing in vehicles, we need to think about the relationship between the perception actions that are done by the embedded vision system and the control system. So I'm going to tell you about some work my students have done, two aspects of this. One, my student Krishna Muva, along with Justin Bradley, on the relationship between latency and accuracy. And then my student Deep Samal and some of our colleagues on a Markovian model for errors in embedded vision. So this thing is not showing me.
Yeah, it shows there.
Right. Okay. Let me look over here. How's that?
Yeah, turn it a little bit.
Okay. So, Krishna put together a code simulator, hooked up AirSim with a control algorithm and some computer vision. He was using the Intel Compute Stick to do the vision. Asked me later how ugly this setup is and how we made sure he wasn't going to take 100 years to graduate. But we wanted to look at the relationship between latency and control performance and the effects of accuracy on that. So this experiment was done with RCNN, which is a more accurate network. It's also tends to be slower. Okay, so this is one test run. We ran it at two different rates. Well, excuse me, three different rates: 1 Hertz, 2 Hertz, and 3 Hertz. This is a complete loss here. The up and down arrows are when it goes in and goes out. And you can see that it didn't really work at all, even at 3 frames a second. Okay, it kept losing the target. Okay, oh, excuse me. So the problem is you've got a chase drone, you've got a target drone. You want the chase drone to follow the target drone, no matter how it maneuvers. Okay. Now, this is SSD, which is faster, somewhat less accurate. You know, it's pretty good, but it's a little bit less accurate. It can run at faster frame rates. So this experiment shows 5 Hertz, 10 Hertz, 20 Hertz, 30 Hertz. You can see 5 Hertz worked, but it was a little marginal. You get up to 10 Hertz, it tracks pretty well. And running faster doesn't help you with tracking accuracy. Okay? So this shows you on the SSD case, this is think of this as a plot between frame rate and velocity as the two axes, and then the tracking accuracy as the z-axis. And so there is a region in the bottom left where it just doesn't work. And then there is the green region where it does work. And you can see that in the top right, it plateaus off. Okay. So on the one hand, latency is important, right? If you're running too slow, the control system will not work. On the other hand, chasing chasing latency also is not at the high end, doesn't buy you that much. You need to be fast enough, and then within that you need to be pretty good. Okay, so let's move on to the question of what is the actual error model here. Okay, I think a lot of people really implicitly assume that frames in this perception, the errors in detecting something and in localizing it, those errors are IID. Okay. Now, if you're dealing with images you get off the web, that's a perfectly reasonable assumption, right? Because they're uncorrelated. But, we have shown through these experiments that in fact, the errors between successive frames in a perception system are in fact Markovian. Okay. And if you get an error in if you don't detect in one frame, there's a reasonable chance you're not going to detect in the next frame. And that has profound implications for control. Okay. So this is the example that got me thinking about this. So here is a schematic version of a target drone. Okay. You detect it. It's flying straight and level. Okay. The target decides to bank. It's part of a turn. Okay. In the frame here, it doesn't get detected. Why? Well, a lot of drones have very complex shapes. There's a lot of different poses. Okay. On top of that, there might be lighting variations and so forth. No matter what you say, well, I could do this to make it better, I can come up with another scenario where, in fact, it's going to be hard. So we should expect that in some cases, realistic cases, that in outdoor environments, we're not going to detect all the time, right? So in the middle frame, we didn't detect. Now we go to the next frame. What is the drone doing? Well, it's continuing its bank. Okay. It's still it's in a different odd position, but it's in an odd position. What do you think the computer vision system is going to do? You think magically it's going to detect in this third frame? No. It's going to continue to, there's a good chance it'll miss. Okay. So because objects in the physical world have continuity, the detection acts in our perception system are related frame to frame. Okay. A lot of people seem to get worked up about this, and they seem to fight this notion. I really don't know why, but I think when you just step back for a second, think about it, it makes sense. But let's try to quantify this. Well, let me go on for a second. So, the methodology that Deep is proposing is to first model the errors given your neural network, given probably some parameters about the use case, about how far away things are and weather and all that stuff, and try to model the nature of the errors that the perception system uses. That is a precursor to what you really care about in the vehicle, which is safety analysis. Okay, so if you don't understand the error model for perception, you cannot do a valid safety analysis. Okay, if you're making assumptions about the perception that are wrong, your safety analysis will not give you plausible results. Okay. And so this is not directly, the safety analysis is not directly part of what I'm talking about here, but my colleague Dun Tran is well known for his work in safety analysis, and we think that this is an important aspect of that bigger safety problem. So this shows you let me go ahead for a second. This is a hidden Markov model that Deep trained on some realistic data. Okay, so he found that given ground truth on the detections in this data set, and given the neural network, that it had 4 states. Okay, and 2 of those states are actually correspond to not seeing it. Okay, so in this case, states 1 and 3 are associated with no detect. And if you look at the transition matrix here, you'll see that these states are very sticky. The diagonal has high probability, the off diagonal has low probability. Okay, if the errors in the frame were IID, this matrix would be much more uniform. Okay. So the bar graph on the left shows you results from several different neural networks, shows you, 4 to 5 states works well, and that's using Bayesian information criterion. This graph on the right, it takes some practice to interpret, but it shows you what a IID model, a recall model, will do, where it thinks that the frames will be detected. It shows you, and that's the gray. It shows you in the orange where the HMM model says you're going to detect or not detect, and then it shows you ground truth in the blue. And the HMM model did a much better job of predicting ground truth than did the IID model. Okay. This also is another way of looking at the state space design. This is 2 different ways to model error Bayesian information criteria and log likelihood. And they both come up with the same basic result, which is, 4-ish kinds of states in the model. Okay. So this graph shows you an example run. Okay. The orange line is the angular speed of the target drone. Okay. So that's part of the ground truth. The big spike in the middle at about frame 200 is where it executes a bank. Okay, so that's a big turn. Given our hypothesis about where we're going to see errors, that's an example of where we might expect things to start going bad. Okay, now we have, once again, 3 measurements of where the vision system thinks things are going. There's the recall, the independent model, which is gray. There's the HMM, which is yellow, and then the ground truth, which is blue. Okay, so what actually happens is the blue line, which is that the position error increases. The position error increases because the target's making a turn. Okay, the IID model is the gray line. It says, "Oh, I'm fine. I'm tracking really well." Okay, the HMM model isn't right on top of the blue, but it gives you, it's pretty good, right? And it's telling you, oh, you know what? You've got some error here. Okay. So the assumptions you make about frequency of errors and correlations between errors have really profound implications for the control system. Okay. And this shows you, for several different examples, that the HMM model gives you much lower position errors in several different examples than the recall model. This person model, they were both about the same. So let's think about what this means for control systems. If you get an error, you're probably going to get it for a couple of frames before you get back to locking onto the target. Okay. That means that your frame rate, your sample rate for perception is effectively reduced. Okay. Now, of course, because if you're missing samples occasionally, there's some amount of stochasticity in the sample rate, but this is more serious than that. Okay. we have the hidden Markov model tells us how often we're going to miss samples and how long that window is. Let me actually go back for a second and show this to you. So if you look on the left-hand side, you can see the HMM model tells you that there are two windows there where you're going to have an extended period where you're not going to detect. Okay? So that looks like a reduced sample rate to the control system. Okay? And this gets back to the safety analysis. Your control system isn't running, the sensor for your control system isn't running at the sample rate that you put in a constant in your code, right? The sample rate in your closed loop system is running at this lower, the perception system is running at this lower sample rate. Okay? So if you're designing the control system based on this false notion of a higher sample rate, everything you derive from that is going to be wrong, right? So this is a slightly different angle on this relationship between accuracy and latency and so forth in perception and control systems. This adds this other dimension of effective sample rate. So with that, I think I've said what I need to say. Thank you so much, and questions, please.
Let's thank our speaker. Questions, please.
I think that the sample rate is not only reduced, but it's also variable.
Well, yes, that's right. That's right. Yes.
So can you use the HMM to predict to a controller when the variability happens so that you can adapt the controller?
So the question is, can you use the HMM to detect when you're going to basically have problems? That's not really how it works, right? Because it's not looking directly at the pixels, right? So once you have an error, right, it will give you some statistics about how long that failure is going to last, right? But it won't tell you, oh, in the next frame, you're probably going to mess up. Okay. Now, could you instrument the neural network to tell you, I'm having problems here and this could go south at any time? We spent some time banging our heads against that problem, and we have not made as much progress as we would like. Right. Well, we have some interesting results, but they're a little hard to, we're not confident enough yet that we can do that. But that's really what you want to do, right? You want the perception system to itself to look at features, combinations of features and say, this current frame here is a little tough for me, right? And so I'm less confident in my analysis here. And so, the next frame, I don't know what's going to happen.
Just a short comment, question. So you mentioned latency is a problem.
Yes.
So do you mean latency or the jitter? So because you can just move the time by delta for control, but probably it's the jitter in the latency.
Well, they're both problems, right? So here we're not in this set of experiments, the failures to detect, right, sort of add some jitter in the sample rate, but the rate at which you can perform that action varies, right? That latency, right? So it's the time from when you put the pixels in the neural network to the time it gives you the bounding box, right? And I I think it would be tempting to assume that if you can if you have a more accurate neural network, that's better for control. But that's not, it's more complicated than that, right? Because the time it takes you to do that is an important aspect in the overall accuracy of the control system. And you know, there is a loose relationship between this and phase delay in a classical control system, right? We know if you crank up the phase delay enough, the whole system goes unstable, right? Yeah.
Okay, one last question. Maybe.
Well, let me say that one of the first things that my students did when we started to think about embedded computer vision at the dawn of the millennium was the world's most expensive PowerPoint advanced button, right? So you do this and it goes to the next slide. We moved on from that.
I still don't have it.
Yeah, well, that's true. That's that is true. Very good.
Well, let's thank our speaker.
Thank you so much. Thank you.
So now we will start our lightning presentations. And please look at, you know, when your time is up coming to present, please be ready to come over here. So let's see. Okay. Is this going to work? Okay, very good. So we are in the presentation mode, I believe. Let's do the mouse. Okay, please join us and go ahead. It's going to start in a second.
Okay. Okay. Hi, my name is Jamie Lim. I'm happy to introduce our work at Qualcomm called SciFlow. So this is a method to enhance lightweight optical flow models with self-cleaning iterations. So optical flow is a problem to estimate the dense motion estimation with the measurement of the pixel-wise pixel displacements from frame to frame. And since the introduction of RAT in 2020, the new paradigm is to use iterative refinement using the COM-GRU. So even though this method works well, there is a problem that we noticed, which is, like many of us know, the error propagation, which can go from one frame, like particularly in the earlier frame, and that stick around to the later frames, and without fixing the problems. So we're trying to solve this problem with two proposals. The first proposal is called self-cleaning iterations, where we try to leverage the temporal feature consistency with reprojection error. So we try to warp the features from frame to frame, and then to use that consistency to really enable the self-cleaning capability for the network without any ground truths in runtime. And then the second techniques that we introduced is called regression focal loss, which is we were inspired by the typical standard focal loss typically used in the segmentation to address the class imbalance problem using the cross entropy loss. And then we borrow that to to address the problem of, instead of the class imbalance problem, we address the difficulty imbalance problem by addressing the difficult areas of the residual errors to further clean up the errors. So here you can see three models. The first one is the base model on the left, and the middle one is using our method of HCI, and the right one is using both HCI and RFL. So you can see that starting from the very first iteration, all three of them are suffering from the strong ambiguities in the estimates. But then along with the iterations, our method can help clean up the ambiguity, particularly around the legs and the arm with not only the small resolution, but also fast motions for the optical flow estimation. So you can see that our method was able to achieve much cleaner method using the self-cleaning and also the regression focal loss method. So I'm happy to answer more questions. Please stop by the posters number 66. Thank you.
Okay, so hi, I'm Alberto. I'm going to present the work with the very long title that you cannot even read on top of the slide, but don't worry because we are going to break it down into 3 different slides. So what we are doing is on-device continual learning on very tiny embedded devices, in particular microcontrollers. And to tackle this problem, what we are doing is we are using both latent replay, so just updating the latest part of a network, and sparse updates. So updating just a fraction of the weights for each layer of your network. And in particular for these 2 strategies, we are merging them and we are describing each update with an analytical cost model. So we have these analytical functions that give us the number of operations and the amount of memory that you need to perform for each update. So this is our network, okay, and our network is called FiNet. And FiNet is very interesting because it's a network that allows you to use these analytical equations to correctly size the network for your target device. Okay. Previously, in previous works, we have analyzed the behavior of this network for inference only, so not training. And we used this equation that gave us the number of operations, the latency, the memory usage. And with these numbers, you could size the network for a target device. Now we are also extending the work for the training step. So with the equations that I showed before, we can also size the network in such a way that you can achieve the best possible trade-offs of performance and reach the best possible performance on your target device. So this is our target device. It is called PULP. It stands for Parallel Ultra Low Power. And it is an array of 8 RISC-V cores working in parallel, okay? And on this device, what we managed to achieve was learning of a new task in the Core 50 dataset directly on the device in under 3 minutes. And not only that, but another great achievement was the fact that we managed to achieve a better trade-offs in terms of accuracy over latency and accuracy over memory consumption compared to previous approaches. So just updating the classifier layer or updating the full network. And not only that, but we also achieved a very big memory reduction going from around 200 megabytes for training to around 2 megabytes for one step. And that.
Right. Okay. Hi. So this is the work we're doing at the University of Manchester, and also we have a spin-out company now called Vision Chip. And what we're doing is we building. So this is a hardware demonstration, not a poster, and we're building the sensor image sensors where in each pixel we put a microprocessor, and so you have this kind of software programmable substrate that can compute on the focal plane in the sensor. So it's like a nearest neighbor connected SIMD array, but it's enmeshed into the image sensor fabric. And so you can compute on the sensor, and what you can output is not the images, you output, well, whatever the results of the computations are. So that could be points of interest, it could be a classification result or whatever. And if you do it, then you eliminate all the data movements. And so you end up with something that is very efficient in terms of either the speed, because you just send the data straight to the processor array, or very low power, because you don't move data around. And so we have a whole bunch of kind of demonstrations that we have done. You can compute optic flow, you can do eye tracking, for instance, or you can do face detection, you can build some kind of video analytics application, you can count people going up and down the road, you can do gesture recognition, you can do digit classification, and so forth. And all these things, I mean, I'm showing here gray level images. Normally, those images don't even leave the sensor. So the images stay there. So it's not even like on the camera, it's on the sensor itself. And all you output is just the results of computation. And I guess there's the kind of research problem here also, like what do you actually want to compute then on the sensor? And what do you want to compute of the sensor and how you partition the entire application? So we actually also have a paper in the main conference about how we kind of learn what should be done on sensor, what should be done off sensors. But in terms of the application that is shown downstairs, we show with one thing, which is a key point extractor and a feature tracker. So what we do is we capture the image, detect the key points, find the good key points, and then track them, kind of label key points, and then output just the coordinates of where the key points are. And because we then reduce the bandwidth, you don't have to send the images at all, you only send like less than a kilobit of data per frame. So we can run it super fast. We run it at 3,000 frames a second. So you can shake your camera like crazy, and you can keep a good tracking of all your features because it runs at a very high speed. So I guess that's that's it. I'm faster
Thank
than
you.
I should have been.
Thank you.
Hello, I'm Luca Bompani, and so in embedded system, smart surveillance, like smart surveillance cameras or nano drones, what they usually have is a microcontroller as a processing platform. And what you usually do with this kind of platform is that you run an object detector on the frames. This is your video object detection, and for each frame, you obtain a bounding box for each of the frame. But this state-of-the-art frame-by-frame approaches typically have to do trade-off between the frame resolution, the detector accuracy, and the throughput. Each frame requires the same amount of computation despite not carrying the same, let's say, information for all of them are not equally important. And each frame is processed independently, so there is no temporal correlation. So if you want, how can we achieve high throughput and high accuracy video object detection on this kind of platforms, so microcontrollers? We created a framework which we call multi-resolution ByTrack, in short MR2 ByTrack, and we present our two main contributions. The first one here, we change the resolution of our object detector, and we match the detections across the frames. Thanks to a tracker, this matching allows us to recover part of the lost information. And so in the case of a mistake in the classification, thanks to the tracker that allows us to bring the information across time, we can rescore, so correct the possible detections, thanks to the temporal consistency. The tracker, as you can see here, is created by the intersection of a reunion, so it's based on the on the position of our detection. So if we have a sufficient matching, we can generate the tracker. The tracker brings the the detection across time, and then we use the rescore to change the classification in the case of a wrong detection. Overall, we deployed our system on the GAP9 MCU. Here you see it is. It's a very limited system with only 128 kilobytes of L1 memories. It has 10 cores for computations, of which and 5 floating point units, and it usually consumes around 60 milliwatts of power, so 100 times less than a mobile GPUs. Here are our results. Here are our baselines. We selected the NanoNet Plus and YOLO X Nano as they are very low, consume very low memory, and they are adapted for the deployment on this kind of platform. If we introduce our method by interleaving 320 by 320 to 192 to 192 images, we are able to improve the FPS and the accuracy of our method with very limited increase in memory. In fact, we reach 2.2 increase in MIP while increasing the throughput by 2.6 FPS, and with only an increase in memory of around 7%. And that's all.
All right. You could feel the excitement. So now our colleagues from Israel were not able to travel, so they recorded a video, and let's see if I'm going to be able to do it here. Okay. Okay, so hopefully this will work. It worked before the start. Do like this. Oh, here. See the screen.
Hi, my name is Raz, and today I will present to you our latest work, ED-DCFNet, an unsupervised encoder-decoder neural model for event-driven feature extraction and object tracking. Event Camera is a novel sensor
So I shared the sound. Maybe start from scratch by doing this. And then doing this.
Hi, my name is Raz, and today I will present to you our latest work, ED-DCFNet, an unsupervised encoder-decoder neural model for event-driven feature extraction and object tracking.
I made it worse.
Event camera is
So
a
I
novel sensor that
apologize to our
measures only
colleagues in
motion in
Israel. I
scene.
did my
This new
best,
camera is based on
but we are
asynchronous
going to move
pixels
on.
with high dynamic range that outputs binary changes
With
according to
many
the intensity change
apologies.
in the
At least
scene.
they had their
The
paper
rate of
published.
each pixel output is about 1 microsecond and has ultra low power
So
consumption. This camera also
you want to
outputs
try
great
something?
frames, additional usage. Therefore, this camera is optimal for object tracking. Frame contains a lot of information, contrary to events, but events capture the changes. Therefore, by using both, the tracker's scores improves.
No.
Furthermore, we created a new,
I give
fully
up on
annotated
this.
indoor dataset.
It worked at the dry
Our
run, but
framework
not
is
now.
based on
So exactly.
UDT and DCFNet. First, we take events between frames and create a voxel from them, and
But so
take
far we are
their
doing great.
corresponding frames. We
This
do it
was
3 times in order to create our sequence.
but
For each voxel and
we
frame,
continue.
we use a
Okay, so do we have somebody for paper number 20? I guess not. So we move on to 21. Okay, I will. Do we have anybody for paper 21? Okay, please join us here. I'll share the screen here. Oh, this is it. Okay. Share the screen. Screen 2. Do you see it? Help me out here.
How many PhD?
Okay, so we have this slide.
Just stop sharing and share again.
Share again. Okay, so should be screen 2, no?
Do you do it?
Okay.
Share. Finish it full screen.
Okay, anybody has a joke to tell?
Yeah. Stop sharing first.
Oh, it seems like the video is still on that screen. So let's.
So how can we stop the video?
Yeah, let me try that.
No, that's recording.
I apologize. Let me try that. Okay, so we need to go back here. Fill this.
Excuse me,
Let's try that
I'm
again.
here for paper number 20.
So with PPT. Just a second. So can we see? Yeah, that's good news. We just need to wait for it to load. Okay, paper 13, your paper number 20.
Yes.
Okay, I think we're back in business.
Share the screen.
Share the screen. Where do we do that? Okay. Share screen. Screen 2. There. And don't worry, we'll go back to your screen. Looks good. Yeah, but we need to go back to. Oh. that slide. Unshare again. Do you know any jokes? While I do this.
Maybe you can ask Nabil. Anything to say?
Okay, you want to try? You know, maybe we'll share this screen and.
Maybe.
Okay, take it away.
Okay, perfect. So, hello everyone, I'm Parak Agarwal, and I'll be, is it good?
Yeah.
So, I'm Parak Agarwal, and I'm from Texas Instruments, and I'll be talking our work on network sparsity. So, sparsity is a very good way of obtaining a smaller network in which we prune out few weights by making them zero. So, in the traditional approaches, what people do is they just prune out, like remove few weights, make them zero, and let the other weights retrain or regain the other information. However, in soft pruning approach, we don't prune out the weights in general. We prune out across epochs so that we have a higher optimization space and thus we get better accuracy. So how do we do this soft pruning is using a technique called weight blending. So in weight blending, we can select any of the weights that we want to prune out on the basis of norms or FPGM or depends on any stream, like whichever type of sparsity you want, you can select the weights you want to prune out. And then we parameterize those weights using the alpha factor or alpha raised by P. So what alpha factor is, it's a function of current epoch. So with epochs, the weights get reduced over time. And P is basically the pace of pruning, how fast we want to prune the weights in the initial epochs versus the final epochs. So we have seen a higher value of P is more desirable for more complex tasks. So yeah. And then finally, after obtaining like the complete prune weights, we allow the network to retrain after obtaining the full sparsity to like get the final accuracy. So yeah, our model optimization toolkit basically supports sparsification of deep neural networks currently, and we are currently working on making it generalizable to transformers. And so in sparsification, we reduce the total number of epochs and thus we decrease the latency. And if the hardware supports, then the data transfer engines and the compute engines can benefit from NSP pruning. But to benefit from channel pruning, so channel pruning is an inference engine agnostic method, but to benefit from it, it's very much required to have a connection over channel pruning. So in type of residual networks, we need to prune out the same input channels. Yeah, so that has been our work, and you can check out our poster and you can scan the QR code for the source code and how you can actually prune out your own networks and try that out. Thank you.
Okay, thank you.
Hello everyone, my name is Omkar. I am a PhD student at Purdue University, and I will be presenting on content-aware input scaling for efficient deep learning, edge offloading. So AI on edge is challenging due to compute, storage, and energy demands. Computation offloading offers a solution to this, wherein we send the input data to a server, wherein the deep learning computation takes place. However, there is an overhead of communication here. Therefore, we propose content-aware input scaling, so that we achieve a good trade-off between the latency and the accuracy. So the overall idea here is that we would like to retain the resolution of the important regions of interest that are present in the image. For example, for the case of face identification, what we would like to have is preserve the input resolution of the facial regions in an image. Therefore, we selectively downscale the image so that the background gets blurred, but the important regions of interest are preserved. And this is done by using a very lightweight convolutional neural network that we have trained that outputs the regions of interest directly. And these are deployed on the edge device directly. And with this selective downscaling approach, we are able to achieve a better trade-off between accuracy and the latency. In terms of results, we achieve around 17% improvement for face identification task on IMDb face dataset. Similarly, we show generalization of this approach to other tasks. So we also tested this approach for key point detection and person segmentation. And in both these tasks, we achieved a gain in mean average precision. Yeah, with this, I would like to acknowledge our sponsors and our collaborators here. Thank you so much.
Okay. All right. Despite everything, we are doing okay with time. The next invited speaker is Jan Ernst. Please join us here and let me open your slides. Yeah, you will be driving the presentation. This one is not timed. Do we see it there? Okay. But it's not on screen. It's okay. Okay. All right. Oh, that's a problem. Where is PowerPoint when you need it? Let's see, display settings, probably. Duplicate. All right. That better? Okay. Go ahead.
Nothing full mode.
Is it on the full screen?
So this is PDF or
PDF? Yeah.
where it opened in PowerPoint. Okay.
Okay, perfect. The wrong presentation.
Wow.
I mean, I'm happy to talk without slides.
Yeah, maybe you can start introducing yourself.
All right, let's get started. My name is Jan Ernst. I'm going to talk about moving from piecemeal ML design to agile design exploration for building ML systems.
Maybe not yet.
Maybe not. Right. Let that sink in for now. Right. Think about it. Come up with good questions.
I had to say I think this is it.
It's good. Good. Perfect. All right. So thanks for giving the opportunity to speak on this topic. I won't go too much into my background. If you pay attention, you can read out a little bit where I'm coming from, shaped by experiences type of stuff. So in a sense, the main thesis of this work is that current ML systems design isn't even design, it's not systematic, and it's done in a piecemeal fashion, right? You make certain choices, optimize locally, try to get the best out, and then you move forward. Yeah. It's single-use optimization, right, where you're optimizing for a particular purpose, but once that is done, you can't reuse that optimization. You're learning something, but you can't really reuse the learning. Yeah. A hallmark type of sentence that you'll find stated there is, let's use this and this architecture with this and this thing and so on. And then you take a step back and ask why, right? Why are you doing this in the first place, right? You don't know. Okay, so we're advocating to move to a thing that is closer to agile design space exploration, yeah, where you're able to learn from anything that you do over time, integrating your evidence that you're learning. And a hallmark sentence where we want to go in this case is basically, let's aim at particular performance criteria, right? Something that you know are meaningful criteria to you, yeah? choices that are meaningful, no matter what kind of experimentation you make. Not necessarily saying that this is the end result, but the starting point. So a lot of this is about good starting points. And the ingredient here that we're adding is basically adding semantics and automation to the ML system design. A lot of this work draws inspiration from two main topics, which is component-based software engineering, which is about building systems that have particular nice properties that we would like our ML systems to have, and product lifecycle management, which is about building products that have certain nice properties that we would like our systems to have. We're not very dogmatic about this, a bit hand-wavy, but you'll see a lot of the reflections of these topics there, and some comment here. Let me see if I can. Okay. All right. So let's get started by looking at a particular product development pipeline. Not to say that this is the only perspective, but it's helpful to understand what the pains may be and where they're coming from. So some of this may resonate with you, some things not. So let's say I start with a new problem. I want to build the next cool gadget, a drone that does this and that, or a consumer product that does this and that. Lots of things, right? Just look out of the door and you'll see all of these things. Generally, right, I start with some data and I have a vision of this is going to be my product in the field, right? Even after a couple of product iterations, maybe. Along this pipeline, you have a set of discrete steps, typically. Things like engineering the data, building your model, doing system integration, right? We heard about latency in system integration and so on, all the way to deployment. Each of these steps needs a lot of decisions, right? You need to figure out, is my data good enough? What kind of architecture should I choose? What hardware do I need to run? How do I update the model, or how do I update the hardware in the field, right? More often than not, these are siloed, right? That's more an organizational kind of thing, but you have to recognize that they are siloed, yeah? Meaning somebody builds the best model and it's super fast and it does it, and they're happy. They throw it over a wall, it lands in the next place, and they have to deal with it. And they can't go back. Nobody likes to take stuff back. So you see already that's more of a feed-forward type thing that is happening in the development there. And then even worse, right? Once your product hits the field, you want to learn something for the next product iteration. Maybe you don't expect it to work 100%, but you need to do some learnings, right? Where do they end up? You have no idea. Yeah, then maybe your data isn't enough. So you got to go back all the way back to the data. Maybe the model isn't fast enough on your particular hardware target after the fact. So do you go back to the model? Do you build a smaller model? Do you change the hardware to make it more performant? These are all options and alternatives, and you have to choose between them. Generally, the issue is that you have a waterfall-like process, right? Which is linear and sequential, basically a feed-forward type of thing. And there are a couple of pains associated with that. Yeah. We've noted here downstream pains and upstream pains, right? Downstream pain basically means I'm upstream in the pipeline and I have to make a decision. I have to choose which model. I have to choose, is the data enough? Do I need augmentation and so on? But you cannot gauge the downstream effects. You don't know how it's going to behave once it's in the overall system. And the same down the road, right? If you build your first system, right, everything end to end, you have it deployed, and then you figure out, okay, I have to change a decision that was made somewhere along the pipeline earlier. How do you do that, right? How do you feed that evidence back into the system? So in order to make progress, here is kind of a picture of this design space as it is at the moment. Yeah, and design space means nothing else than it's all the parameters, all the choices, and all of the things from the data to the field over a decade or so, the lifetime of your product you may need to make. Yeah? And each of them has gazillions of parameters. There is new models coming out, new compilers, new hardware. Yeah. Particular example, if you go out here, right, everybody's saying, oh, my model is hallucinating, right? Gen AI, LLMs, they're worried about hallucination. Sure, it's a problem. How much hallucination can you take, right? How do you say this is how much I can take to trade off my system accuracy? And we'll get back to this later a bit. So how can we improve this, right? And where we want to go basically is to say not I choose this particular model, but to say from the get-go, how well will it work for my application? So a bit of a predictive aspect in there before I even kick off the first training. Maybe it's important for you to understand how much the training costs, right? Maybe it makes sense to first train a smaller model to unblock the downstream product design, and then later come back and do the same thing, only with a more powerful training architecture and so on, where you can spend the time. So there is also a temporal aspect there. When do you make which decision? When do you have to make which decision? And generally things like, how can I trade off certain aspects of my design? Speed, accuracy, for instance. I believe the topic of trade-offs is important enough to warrant a quick detour. Yeah. So we already looked at accuracy speed trade-off. It's a very fundamental thing, right? You see this in every paper, or at least papers that take empirical evaluation serious, right? They understand that there is a trade-off, and you gotta talk about it, right? And there is many more trade-offs, all the way to how much can I hallucinate versus how effectively can I still solve my problem. So, as all of you are very well aware, this leads to a view where we have a multidimensional Pareto frontier of optimal models, right? And every design or ML system that is on that frontier is optimal in some sense. It's an optimal trade-off between all of the dimension. And what we want to achieve here is that you can navigate this Pareto bound here in a meaningful and natural way, basically. So we're going to do this in two distinct steps. The first step is to take the design space as it is and add certain semantic abstractions on top of this. What this gives you is the ability to automate algorithms, meta algorithms, basically on the system design space. And I'll give a couple of examples how that looks like. Once you have an automatable design space, you add automation. And then you can move towards what is stated here as evidence-based design, right? You're designing not what you think or what the latest paper says, but what you have evidenced in the past from a big database, essentially. And overall, this should allow you to make the step from local design choices without information to evidence-based design that allows you to talk about your performance criteria. So let's see how we get there. First step is adding semantic abstractions. Fairly straightforward. You look at all of the various components that are there in your system design, and you find a common semantic description scheme. There is probably many ways to do this. Doesn't matter so much, but you need a way to express this in a semantic way. That means you need to talk about a taxonomy of components. And there may be many taxonomies. Again, it's a fairly irrelevant detail. What you end up is what we've come to call a ML systems recipe. Here, an example of a taxonomy, right, which is hierarchical, it's tree-like, and any component of a system can be put somewhere. This is a way to allow you to talk about long-range dependencies between components. And then finally, a recipe itself is nothing else than a tree of categories in that taxonomy. Has a lot of nice properties. As we mentioned already, it comprehensively describes the full system, including actions that you can take on the system, like training, visualizing, deploying, and so on. It's unambiguous, so there is a one-to-one relation between the space of all possible recipes and that representation. It's hierarchical, compositional, and so on. Let me highlight a couple of nice properties that has. So the first one, and this is the most important one in a sense, because this is what we set out to achieve in the first place, is that it's programmatic. So this is literally accessible in Python, right? Where you can hack away, and that means modeling your system and describing your system. So it's a system description language in some sense. And via the semantics, you can do a couple of cool things. For instance, introspection. The way to think about it is, let me start specifying the system. Maybe you know something about the particular models that you want to use, right? So for instance, you know that you have a detection problem. Yeah. So you feed in detection data, and then the system can tell you, these are the choices that are available to you, right? You told me you have detection data, so I'm only going to allow you to use detector models. Yeah. And again, this makes it feasible to automate because you can formulate meta algorithms over this layer of abstraction of system choices. Another example to the right here, you see how to loop through model families and all backbones. Let's say if this is your system in 5 lines of code and training them. And this piece of code works no matter what kind of space you're looking at, right? Classification, detection, LLMs, anything. You can mix and match, right? Somebody can find a nice component here, they can throw it in, and it's available to you. I won't go into too much detail on some of these for the sake of time, but all of this is fairly implementation agnostic, so I can throw in a particular component that has a template, right? It's well-defined interfaces, it describes its own business logic, and it can kind of voice out what it can do. So for instance, an detector model, right? An efficient DET, right? Says, I need bounding boxes. Yeah, this is how to train me, right? And then I can put a trainer in and run the particular actions on that model. And that it's maybe Python or PyTorch or PyTorch Lite or YAML underneath can change, and you don't have to worry about that. A nice thing about this in practice is that it's serializable, so you can convert it to a string. You can share the string, use it for deduplication because we have full reproducibility. So if you feed the same string into training twice, you get the same result. If you feed it into deployment twice, you get the same result guaranteed. You can store it in a database. If you're from Germany, you can send it by fax because this is how we do things there. Anyways, so already mentioned, right, compositionality and I have the hierarchical nature that is inherited by the taxonomy basically, and the tree-like structure, which makes it super easy to formulate complex algorithm based on a space of system design. So if you have space in mind and you want to train all of them under certain optimization, something like this, it's just a couple of lines of code essentially. We already talked about a little bit about the semantic nature, right? There is a bunch of semantic relations which relate components for various purposes. All right, so now this is the end of the first step, right? We defined a way to describe a space of systems. And this is more about the design, right? This is more about what is there in a semantically meaningful way so that I don't have to worry about the particular instance details. And that is now describing the space. Now the second step basically is essentially mining, right? Now it's as simple as coming up with all the performance criteria that you may want to glean. How big is the model? How fast is the model? How well does it work according to whatever task metric you have? What is the latency, right? All of these pieces. And the key thing here is that because we have the semantic link, we can directly relate any insight that we get from these performance evaluations back into the semantic space. So how does it look like? We have this design space. Now we sample a recipe, right? Recipe literally is this tree-like structure. And then we have various execution engines. For instance, training you can do with PyTorch, TensorFlow. You need to compile a model. There is a bunch of compilers. You need to do this and that, right? So you can throw hardware at it, compute hardware, inference hardware of various kinds, right? From microcontroller all the way up to data center GPU, and then start gathering metrics. And that essentially, if you do that often enough, translates that design space into a performance space, which is nothing else than noting down all of these performance characteristics, but linked back to the design space in a semantic manner. So I can ask, for instance, over all experiments, all objectives, all data, how much does S3D work better than Adam? Yeah. Closing the loop with the earlier argument, right? Now that performance space has a Pareto optimal boundary, and I can now empirically measure it by just identifying all experiments that are on that boundary. And we've been running on the order of tens of millions of those experiments, each of them being a complete ML system from data to field.
across different objectives, across data, and so on. Now, to come to a close, let me show you a couple of slices of that data. You see here basically this Pareto trade-off. This is literally what you're seeing here. So again, the way that it works is that I tell you whatever I think I know about my design so far. For instance, here, what I know is that I have data that is reasonably complex, well sampled, but doesn't have a lot of bias. As an example data, this is like modern autonomous driving systems, right? They're really well sampled. Maybe a matter of opinion, but compared to other data sets, they are, right? And they don't have a lot of bias. So you can say this complex data, right? You literally specify this, right? You say for the recipe, I believe my data has these and these properties. And then the solution space is already limited to recipes that work well on those data, right? So you already get less data augmentation, perhaps. If you say I have data that is less well sampled, you get more data augmentation empirically, right? This is evidence-based, not guessing, but by looking at these millions and millions of experiments. And then here you also say, okay, I think my target should be some such hardware, right? In AGX, Orin in this case. And then you say what I need at the moment is to look at the trade-off speed versus accuracy, and also give me a sense of the energy usage. And then you get a plot like this. And I'm going to share the URL for this and invite everybody here to have a look at the tool. It's publicly available to look at the data and inspect the data. And here it conveniently plots you your specific Pareto curve already, which is in this case 2-dimensional. This is only because we are only able to do 2, maybe 3 dimensions, right? But everything is there to do this in many dimensions, and you can navigate this programmatically as well, right? You can go along this curve and inspect where you are programmatically. So here you could say, okay, I need at least 300 frames per second for my problem, and then you already know what kind of experiments you should run on your data. This is before any of your data has run. This is before any of your data has run. You have executed nothing at this point except looking at the data, but you can already predict what kind of parameters should you choose to meet these performance requirements. And you can slice it and dice it according to various ways, right? This is now the same setup, but for an Intel CPU. So you can immediately see what kind of frame rate can I get, right? And you can relate to the cost, how much do I want to invest, and then make the right choice before you run the first training. Yeah, here, this is energy per inference versus the relative accuracy and so on. So to summarize, the key thing here is to have a semantic design space on one hand and a performance space that is empirical, run by experimentation on the other hand, and a clear link, right? This way, if you run an experiment, you will always be able to understand what that means because you can keep track. We have full reproducibility. Even 5 years down the road, you'll be able to exactly say what this means, right? You can do things like marginal statistics and conditional queries on this kind of data, right? Across all objectives, what would happen if I move from SGD to some other moment optimizer, for instance, and you can get empirical insight into this. Similarly, if you have your experiment and you would like to know how can I improve it, right? You can use the data to predict what certain movements in that system design state space may make an improvement towards your objective. All right. Again, I invite you to browse the database. It's available at gtc.latentai.io. I also would love to learn about what trade-offs you have in your system and system design. And we've already heard a lot about latency, speed, bandwidth, and these kinds of trade-offs. We have a lot of more things to come based on this. Things like capturing design intent and replaying design intent so that you build a system and we are observing how you're doing this, right? How are you going through the training process and your own evaluation, and then capturing this and being able to replay once things change with new data and so on, which is a natural extension of this. And I invite you to look at our website at latentai.com to learn about upcoming webinars and other material that we can share. Thank you so much for attending.
Thank you. Let's thank our speaker and let's see if there are any questions. Yes.
So I assume this is for a multi-designer, multi-user environment, right? Which brings up, it seems to me then you have data sharing problems that are of an entirely different order of magnitude than even standard MLs, right? So how in practice, how do you navigate those issues?
Right. I mean, that is a question of how do you isolate information, for instance? Oh, microphone, okay. So a lot of this is fairly orthogonal to how you keep your information, right? And how do you isolate your information, right? And in a sense, aggregating all the information that you have in a simple, compact information makes it kind of straightforward to add things like who owns that information, right? And who's privy to this information.
Good question. So the first one, I was missing the domain requirement in the design phase. So you have the goals of your training, and so basically you need this domain requirement. I was missing this. Probably you have it in some of the things. But the second point also is when you have the data space that you are training for. But what happens if you have the data that you didn't anticipate in your design, like new type of data or new models and so on and so forth? So how do you integrate this in the design? Yeah.
Okay, so an important part here is that these are one way to see this as better starting points, right? If you really say you go into new data, and nobody can predict across all data. So you can always come with a counter example. It's absolutely clear, right? A lot of this is about averages. But the idea of capturing whatever you know already, right? You only accumulate knowledge. And if you have truly new data, right, maybe there is an average that you can use from the evidence to predict on your data. And then as you accumulate data from your domain, right, if it's a one-off thing, all bets are off. But if you do it kind of repeatedly, right, and you add in that domain, right, you can gather this information and use it for predictive power as you run your experiments, basically.
Now, I mean, if you would like to integrate continual learning, like if you have got new data, then you continually learn this new data or something. If there is a room to include this, for instance.
Okay, I see. So this would be somewhat like a property of the training system, basically, which you would describe here, right? Yes. So it should be absolutely compatible, right? All of this is extensible. So if you say that you have a particular way of doing this in a continuous manner, right? You still have to specify how you do that, right? What does continual learning mean to you? Where do you cut off the data? How do you measure that you're not drifting away and so on? You still have to do this. But adding this layer allows you to specify this in a way that you can automate basically the whole design flow.
Okay.
This seems to be like a holy grail. So there should be a catch.
A what?
A holy grail, something that is too good to be true.
I'm good at selling. No. So I think it's thank you. There is no magic here, right? This is all old stuff. If you think about it, right? This is all well-known component-based design to decouple and bring in compositionality has been there for 5 decades. Everybody understands Pareto, optimality, and so on. I think if anything, right, is that you have to build up the space piece by piece. And the question is, are you being overtaken by that space growing in a sense, if that makes sense, right? Can I add hardware quick enough if it's while it's being built? This kind of thing. But automation is powerful. And that's kind of my background as well. So automation is powerful, and giving the power of automation to ML system design is a no-brainer. So that is, I think, the the thing, but it's still hard work, right? To identify how do you do it and how do you still spend your time and compute cycles on meaningful things, basically. Yeah.
One last question. And then you can continue with questions afterwards because we have the second poster. You can ask offline. So please.
Yeah, okay. So yeah, I think my question would follow up in that direction a bit, asking about having generalized system that can handle a lot of different cases, usually or in a similar, can handle different cases in a similar fashion, usually somewhat limits the specific like the customizability of the system itself. So if I want to deploy to hardware that is already a challenging problem by itself. So if I switch between hardware platforms, I, for example, want to apply customized pruning quantization flows to that network. So how much can I customize these flows to work with my workflows?
Exactly, right. So there is the generalist specialist trade-off.
Yes.
Again, a trade-off, right? And there is no free lunch.
Yeah.
And no magic to any of this, right? But here the way to think about it is yes, exactly. So you're saying I have some hardware and there are some optimization algorithms. You come with a different hardware. Here you make the hardware available, which is adding this layer of semantics where the hardware can say, I can do this and this, and I'm compatible with this and this optimization. And maybe the optimization at the training stage are tightly linked with the hardware. So only certain pruning algorithms like structured or block sparse works for my hardware. But here you can express this, you can codify these constraints. Basically.
So your framework basically provides interfaces that are somewhat static that I can fill with my own backend.
Exactly. It's exactly that is one part to provide those interfaces, and those interfaces then are meaningful, where you can then put an algorithm on top that says, now I would like to train for something, and maybe I want to use this hardware.
And that is true for all levels also. So I can abstract my own hardware, implement some logic. I can bring building blocks for models.
Exactly. You still have to bring the middleware for the hardware, let's say, right? If you have your compiler for your hardware, I don't know, right? But if you tell me how to compile for your target and so on, right, I can just plug it in, get your hardware, generate results.
Okay, let's thank our speaker. It's time for the second session of posters. Please be back here at 5:30 for the best paper announcement. And that's gonna be it. So go. Posters. If you are online and still listening to us, we'll be back in about 30 minutes with the announcement of the best paper award.
Should we make them the result of sigma?
Yeah, let's do that.
Yeah.
What is your paper? Number
6, I think.
6? No?
No.
No?
22.
No. 9.
Yeah, we need to wait for a few more.
These guys are gonna.
I didn't say anything. Maybe we can check if number 15 is anywhere close by. I do have a rank for, I mean, just.
There.
Yeah, that's right. He's qualified. Okay, so do we need to record this or?
I'm recording. Yeah.
Okay. So let's close this really fast.
Do you want to share the screen?
Oh, because I don't have the link just yet. Let's see. Oh, no. Do we have to go through this again? What the?
Just a moment, please. 5, 4,
5, 4,
8, 9,
8, 9,
2, 3, 9, 1.
2, 3, 9, 1.
Yeah.
Okay, I think I don't need my audio, correct? Okay, share my screen and we'll start. There. Will that work?
I can see this one.
Okay, good. Okay. Quick summary of the day. We had 5 really nice invited talks. Thank you, invited speakers, for joining us. We had 13 papers, 1 demo. We're really proud that we will have full screen.
You can see the.
Don't worry. Don't worry. We're really proud to host, to be guest editors of IJCV, the top computer vision journal, with our special issue. So there will be more information about that. You guys will be invited to contribute. There is no guarantee that it will be accepted. Your paper will be accepted. It will be a rigorous review process, as you know. So without further ado, the paper award goes to paper number 15, Luca. Whoops, not like that. Oh, top secret remained here. Sorry about that. So that's the best paper award. We'll tell Luca. Sadly, there are no awards. I mean, there are no souvenirs. Luca.
Yeah.
Congratulations. So we will send you a PDF, like a best paper thing, and you can print it and you can frame it and you can put it on your wall.
Thank you very much.
Put it on your seat.
I was really not expecting this.
Let's take a picture. Maybe stand there, here, and I'll be here, and I'll shake your hand.
Yeah. Okay. You need to see the name.
Okay.
Maybe it's better. Okay. Congratulations.
Thank you very much.
Sadly, this year we don't have any gifts. Last year we had the nice GPU and stuff. Yeah,
Really?
not this year, sadly. Anyway, congratulations, and we hope to see you again on our workshop. And that's it. Contact us if you want to be a part of our organization committee. Luca, you know, this qualifies you. No questions asked. You want to be a part of it? Tell us. And
Great opportunity. Thank you very much.
thank you. And we hope you enjoy the rest of CVPR. Thank you. You can go now. Yes.
Let's go with that. What's that? Good missing room.
Yeah, sounds good. People, what is it?